Imagine you have a large language model that, if you let it try a coding task 20 different times, actually solves the problem in at least one of those attempts about 99% of the time. That is a real number from this paper on Terminal Bench, a benchmark of long horizon shell tasks. The catch is enormous, though. To capture that 99%, you need a verifier that can look at 20 candidate solutions and reliably pick the one that actually works. Without that verifier, all that latent capability just sits there, invisible. And this is the gap the paper is trying to close. The authors argue that verification, meaning the ability to judge whether a solution is correct, deserves to be treated as its own scaling axis, right alongside pre-training, post-training, and test-time inference scaling. Right now, the two dominant approaches to verification both have serious flaws. The first is what people call LLM-as-a-Judge, where you prompt a language model to output a score, say from 1 to 5, and you take the token it assigned the highest probability to. The problem is that this collapses a rich internal belief distribution into one coarse integer, and when you ask it to compare two decent-looking but subtly different solutions, it just calls them both a 5. On Terminal Bench, this approach ties 27% of the time, which is a disaster for ranking. The second approach is to train a dedicated reward model, but those are expensive, tied to their training distribution, and don't generalize across domains like coding, robotics, and medicine. Their proposal, called LLM-as-a-Verifier, is elegantly simple at its core. Instead of taking the single most likely score token, they extract the full probability distribution over all possible score tokens and compute the expected value. So if the model puts 60% probability on the token 12 and 40% on 13, you get a continuous score of about 12.4, not just 12. Think of it like the difference between a judge who slams down a wooden gavel labeled with one integer versus a scientific instrument that reports a smooth reading with real decimal places. That instrument reveals internal uncertainty and fine distinctions that the gavel destroys. This one change unlocks three scaling axes. The first axis is score granularity. Rather than a 1 to 5 scale, they use a 1 to 20 scale with letter-based tokens, which lets them pull 20 top log probabilities cleanly from the model. Crucially, this doesn't give the verifier new information about the trajectory. It just gives the decoder more room to project its internal belief onto a finer grid. So beliefs that would have been rounded to the same integer now land on distinguishable continuous values. They measure this using a signal-to-noise ratio, comparing the expected score gap between correct and incorrect trajectories against its variance, and they show this ratio climbs as granularity increases. The second axis is repeated evaluation. Even with fine granularity, one forward pass can be biased by quirks of the prompt, so they average across multiple independent evaluations, which is essentially a Monte Carlo estimator whose variance shrinks as 1 over the number of samples. The third axis is criteria decomposition. Instead of asking one big compound question like, is this trajectory correct? They split it into simpler subcriteria, such as does it satisfy the specification? Does the final output format match? And are there any error signals in the logs? Each sub-verification is easier, and their ensemble gives complementary signal. There's a nice concrete case study on a SQL query optimization task. Both candidate solutions produce faster queries, but only the correct one actually validates that the results match the original. The verifier's reasoning trace hedges with phrases like slightly cleaner and marginally more direct. And when you use a discrete 1 to 5 judge over 100 repetitions, it ties 88 times out of 100. Using the expectation over the same 5-point scale eliminates ties completely and ranks the correct trajectory higher 69 times. Scaling granularity to 20 pushes that to 77 correct rankings. Same information, same model, dramatically different discriminating power. Now, once you have this verifier, you need to actually use it to pick the best of n candidates. And comparing all pairs scales quadratically, which gets expensive fast. So they introduce something called probabilistic pivot tournament. The trick has 3 parts: First, they do a ring pass, where candidates are arranged in a random Hamiltonian cycle, and each is scored against its neighbor. So every candidate appears exactly once in slot A and once in slot B of the prompt. This cancels out the well-known positional bias where language models favor whichever answer they see first. Second, they pick the top K candidates from that ring pass as pivots, concentrating the remaining verification budget on the most promising candidates, rather than wasting queries on obvious losers. Third, they run pairwise comparisons of every non-pivot against every pivot, plus all pivot-pivot matchups. Total cost scales linearly, rather than quadratically, and preferences are aggregated using a Bradley-Terry model over the continuous rewards. The experimental results are strong across 4 very different benchmarks with no per-domain fine-tuning. On Terminal Bench V2, they hit 86.5%, beating the current leader GPT 5.5 alone at 84.7. On SWE-Bench Verified, using a heterogeneous pool of 3 candidates from Claude, Gemini, and Minimax, they reach 78.2, above any individual model. On RoboRewardBench, where the input is actually multi-frame video of robotic manipulation, their zero-shot approach hits 87.4% preference accuracy, beating specifically trained reward models like RoboReward8B that saw around 45,000 robot episodes during training. And on MedAgentBench, a simulated electronic health records environment, they push Claude Opus from 70.2 to 73.3. A really interesting side effect is that the continuous verifier score correlates strongly with task progress. As a successful trajectory unfolds step by step, the verifier's score climbs monotonically, while failed trajectories stay flat or drift. They measure this with a Spearman rank correlation between step index and verifier score, and they get 0.85 on successful runs versus 0.77 on failed ones. On robotics rollouts, it reaches 0.966, dramatically higher than existing methods like top reward, which tends to saturate at probability 1 immediately and lose all mid-trajectory resolution. This progress signal has 2 practical uses. They ship it as an extension for Claude Code and Codex, so developers can watch their agents work in real time and abort runs that are stalling. And they use it as a dense reward for reinforcement learning, which addresses the classic credit assignment problem where sparse end-of-episode rewards give the agent almost no useful gradient. On the Libero robotics benchmark, using the verifier's per-step progress as a shaping reward on top of soft actor critic gives roughly 1.8 times better sample efficiency and a higher final success rate. On the math reasoning benchmark with group relative policy optimization, the reasoning quality reward gives about a 10% efficiency gain, which matters especially early in training when all sampled answers are wrong and the group relative advantage would otherwise collapse to 0. There are limitations worth flagging. The whole approach fundamentally depends on being able to extract token-level log probabilities, which frontier commercial models increasingly restrict. Though the authors describe a 2-stage workaround, the verifier still inherits the biases and blind spots of the underlying language model. So on truly novel or adversarial trajectories, it could confidently misrank things. Gains from repeated evaluation diminish, because errors on hard examples are correlated, not independent. And the pivot tournament, while clever, assumes the ring pass reliably surfaces strong candidates as pivots, which might fail when quality differences among candidates are subtle. The Oracle upper bound of 92% on Terminal Bench versus their achieved 86.5 also shows real headroom remains uncaptured. Now let's walk through some questions you might have after hearing all of this. Why does taking the expectation over score tokens actually help, given that the model isn't seeing any new information? The key insight is that the model has a rich internal belief that gets projected onto whatever output space you give it. When you force a discrete 1 to 5 choice, subtle differences in belief that would place one solution at 4.3 and another at 4.6 both round to a 5. Taking the expectation doesn't add information. It just preserves the resolution that was already inside the model's forward pass, resolution that discrete decoding was throwing away. Why does the ring pass matter so much for the pivot tournament? Language models have systematic positional biases, meaning they often favor whichever candidate appears in slot A or slot B of the prompt, and if you don't correct for this, your rankings will be corrupted. By arranging candidates in a random cycle where every candidate appears exactly once in each slot, positional bias contributes equal amounts to every candidate's score and cancels out in expectation. This gives you a clean, unbiased ranking to identify the true top contenders as pivots. Could you get similar gains by just prompting a stronger judge model with a bigger scale, like 1 to 100? Not really, because the fundamental problem with discrete judges is that the argmax operation destroys the underlying probability distribution regardless of the scale. Even with a 1 to 100 scale, if the model is torn between 57 and 58, you get one integer, not the graded uncertainty. The paper's mechanism works because it reads the full distribution before any argmax happens, which is a structurally different operation than making the scale finer. Bringing this to large-scale recommendation systems, there are several immediate connections. The pairwise verification framework with continuous preference scores from Bradley-Terry maps very naturally onto ranking, where you're essentially comparing candidate items for a given user context. Today, most industrial rankers train pointwise or pairwise models on engagement signals, but LLM-as-a-Verifier suggests you could use a frontier model to generate fine-grained preference signals for edge cases, like new items with sparse engagement data, cold start users, or ambiguous queries where behavioral signals are noisy. The expectation over Logits trick is particularly valuable because ranking cares deeply about breaking near ties among high-quality candidates, exactly the regime where discrete judges collapse and continuous verifiers shine. The progress tracking application is also directly relevant to conversational recommenders and multi-turn agent-driven experiences, where you want to know if a user's session is progressing toward a good outcome or drifting. And for reinforcement learning-based rankers, which large platforms are actively deploying, using the verifier as a dense reward signal could dramatically reduce the sample complexity of learning from sparse conversion or session completion signals. The main production concern would be latency and cost, since running 20 log probability extractions with repeated evaluations and criteria decomposition per ranking decision is far too expensive for real-time serving. The realistic play is to use this offline for high-value tasks like generating training labels for cheaper student rankers, evaluating candidate generation strategies, or auditing model behavior on long-tail queries where automated metrics fail.